So this is chapter 32, and there is a lot more in the book, but I'm going to just cover the key concepts because really the chapter 33 is more important and we want to spend a little bit more time there. So we'll talk about just notation here. The notation is open and closed queuing networks, product farm networks, and then how do they apply to computer systems. All right. So most of the computer systems that you will deal with will be a network of queues, not single queues, because the jobs will arrive at some device, then they will go to the other device, and then they will go back to some other device, and so on and so forth. They will be circulating in the system before they get out. So every system most systems actually are queuing networks, not just single queues. And it's like going to a government office. You go to one queue and then you go to the second queue and then go to third queue. So that's what most of the real systems are, computer systems are. And so then we have queuing networks. The question is queuing networks can be of two kinds clearly. One is open. Open means the input comes in to the system and then the output goes out. As opposed to the closed. In the closed, nothing comes in, nothing goes out. Everything is inside the system and it stays inside the system. And basically what we have done is everything that goes out goes in. So the number of jobs in the system is fixed. So where are the closed systems? The closed systems examples are batch systems. You submit 15 jobs, 15 jobs are running, and they're just circulating between the inside, for a long time. And so that would be a closed system. And we'll see, more examples. But anyway, the idea of closed and open is that in the open, there is an out link and there's an in link. But in the closed, the out is connected to the in. There could be hybrid systems too. Hybrid are next, in which for some classes of jobs, there are multiple classes of jobs. For some classes of jobs, the system is open. For some, it is closed. So for example, interactive systems means, you might have a thin client on the desk, and so there are 15 people who are working on a single computer. Right? Everybody understands what a thin client is, right? So really a terminal, nothing else on your desk. And so 15 people, so those number 15 will remain fixed. They will do something, get out, then do some more thinking, do some more, and keep inside the system. Whereas there are some batch jobs running which get in and out. Okay, so that would be mixed system. So let's take a simple network. The simplest network would be a series network. You go to one queue, from there you go to the second queue, from you go to the third queue. Now the interesting thing about this series network is that if this is Poisson, the input is Poisson, what is the output here? Poisson, right. So this is Poisson, everywhere it is Poisson. So even though there are many queues, you could analyze this queue independent of that queue and independent of that queue. So each queue can be analyzed in independence. And so the utilization of the ith server is simply lambda upon mu I. And the probability of ni jobs in that queue is given by mm1 q, 1 minus rho I times rho I raised to ni, where ni is the number of jobs in this queue. In this case, it would be n1, n2 would be the number of jobs in this queue, and nk would be the number of jobs in that queue. So you could analyze all that. And if somebody asks you for the combined probability, what is the probability that there are n1 jobs in the first queue, n2 jobs in the second queue, n3 jobs in the third queue, and nm jobs in the last queue? You can write the probability because they're just independent and the whole thing will multiply together. And so this is the simplest network and we can analyze it fully, and I can ask you about 90 percentile and anything else you want, right? All the statistics is available. But the interesting thing is that the probabilities multiply. The probability of n1, n2, n3, nm is some product of some terms, which are functions of n1, n2, nm. These kinds of networks are called product form networks. This is a very important class of networks which doesn't have to be series, and we will notice that there are many other networks that follow this property that if you have n1, n2, n3, nm, m devices, you can find the combined probability by just multiplying some expressions. Some expressions, they don't have the probability. Some expressions you can multiply and you get it. And these are the most analyzed networks in computer systems. So there are thousands of papers on product farm networks. They don't have the series network. So we are coming up to that one. Before I go to the series networks and more of the product farm networks, here is a quick quiz for you to check out that you understand what we have done so far. So there is a system here in which I have drawn three different boxes, blue, red, and black. And I want you to know, want you to find out whether the blue one, the network C, is open or closed, network B is open or closed, and network A is open or closed. So just write down your answer there. All right, I'm going to move on to the answer. So network A, the big network, is closed because there's nothing going out of it. Network B has some jobs which don't go out and some jobs which go out. B, blue. Sorry, B is red. Right? It contains these admin jobs that don't go out. So it is mixed. And network C clearly is open for both all classes. Both classes, actually, there are two classes here, and it is open for both classes. Which job go out of B? Okay, so B is red, and users 1 and all the users are really out of the system. They are going out of B. These people are also going out of B. They are also going out of C as well. The boundary for the system C is this. If you are modeling this part, and this is the boundary, and then even the admin jobs are going out. All the users are outside of the red boundary. Where is B? What is B? Yeah, so the blue line, it is going out of the blue line here. When you are considering B, you really don't know where they're going, but they're going into B. They're coming out of B. They're going out of B, coming into B. User is outside the system, and that's why this is a mixed one actually, because admin is inside. So there are two grades of administration and the users here, two classes of users. Okay. All right. Now let's go to product farm network. So in general, if a network has this formula where N1, N2, Nm, the combined probability of N1, N2, Nm is some function of N1, N2, Nm and some function of the total N. N is the sum of all the people inside the system, are in the system, right? So if you have a formula like this, it is called a product farm network. And another example of product farm network is this network. This network, the arrival is not Poisson, so we don't know whether we can multiply all this. But whatever number of jobs you put, 4, 5, 6, 7, 8, 9, 10, you can put any number of jobs here. Let's say capital N jobs you put in here. Some of them will be waiting here, some of them will be waiting there, period, done. And as soon as they get out from D2, they come back to D1. They get out of D1, they get to D2. So if this is only if the network is stable. The answer is yes. All of the queuing theory analysis that we will cover in this class is for steady state. There is queuing theory for transients, but that is just too difficult and not for this first level class. Okay. So everything that I say here today or anything I say in this class for the next several days is for steady state. So steady state means if it is not stable, steady state is infinity. So here, basically, we are keeping life simple. We are not losing jobs or killing jobs or anything like that. We just keep things inside the system in a steady state. We get average of a steady state. So in this case, that is the case. The jobs, whatever number of jobs are there, they just stay inside. The formula is here. Now, you don't know how to get the formula, but it is not important. Just this is an example. And so this is the formula for N1 jobs here and N2 jobs here. Somebody derived it. All right. And this follows the product form. Why? Because this expression outside is a function of capital N, not of N1, N2. And this thing inside is a product of N1 and N2 functions. Okay. So whenever you see an expression like this, then you know this is a product form network. And so the first person to analyze product form network was Jackson, 1963. And his result actually was that if you have a network of well, I wouldn't call it MMM, but basically If you have results where you have exponential servers in parallel, and you have any arbitrary network of those exponential servers, then has a product form. Then it has a product form result. So these networks are easy to analyze, just like exponential is easy to analyze, normals are easy to analyze, product forms are easy to analyze. So most of the queuing theory is about product form networks. And if in the previous example, if everything was just single server, rather than M servers, then you can write down, just like the series case, you can write down the probabilities. Then somebody else, 4 years later, Gordon and Newell wrote a paper in which they generalized it, where they had any M server queues with exponentially service time and could also perform. And then a few years later, Basket, Candy, Munds, and Palacios, BCMP, as they are known, they analyzed it and showed that for even broader class, there is this thing. And the book actually goes into details of how these results are different. Okay, what are the things, how they expanded the class. I'm not going to cover that in this class here. That is something that you can read on your own. And under these, all the generalizations, the things may not remain Poisson. So you cannot just say that I will take this in isolation. So analysis becomes much more complex, right? And so we will not do actually that much of analysis, because if we go into queuing theory, you really need to take a queuing theory class, whole semester class on queuing theory. What we will do is we will teach you the analysis that will get you most of the time on the back of the envelope. So you can sit down, somebody asks a question and you say, well, here's my queuing model, here's my result. Back of the envelope. And those techniques I found are much more useful, much more powerful in real life than, going through detailed queuing theory, because many of these assumptions don't apply, such as product form, such as, other things, those are assumptions. Under those assumptions, the result is very accurate. And then you write down 15 pages of math and you give accurate result, but that is accurate for a system that you don't have. And so that kind of mismatch happens. So if you don't have an accurate system, then you might as well give the approximate answer that we have. Okay. So anyway, so one of the models that we use quite often is called machine repair model. In this model, or actually it was used originally very much, because in this model what happened was, and this applied for the batch system. In the batch system, they had a number of users who would submit a job, and then the job came out, they sat down and they thought for some time and then submitted the second job. So what you have is a server, central server, and then you had a number of users who were basically submitting the jobs, right? So this is called machine repairman model. You know why? Because it's like, think about a washing machine company, and I forget the name, very famous one, starting with M. Anyway, so they had a very good record of having, and they advertised on the TV saying that our repairman is sleeping because there are no failures, right? So this is the model that represents the system is just sleeping because the no machine fails. If machine fails, the person went and repaired it and came back. All right. So this is what is happening. This is the repairman, and these are the machines in that sense, right? Repairman model. But for computers, this is the system, and these are the people who are using it. All right. So this is for the batch systems. Then Buzen, who was actually senior to me, 2 years senior to me at Harvard. So basically, he came up. His thesis was this one. Actually, this is very famous model. And his model was called central server model. He extended it a little bit more, that you not only have the repairman here, but you can go to the disks and come back, and you can go to other systems like network and come back, and so on and so forth, and you could have multiple disks. So this is called central server model. Why central server? Because CPU, everything has to go through CPU. You cannot go from A to B without going through CPU. If you want to go from user disk to system disk, what you do is you go from CPU, user disk, come back to the CPU, and then go to the system disk. All right. And similarly, when you want to go back to the terminal, you come back to the CPU and go to the system disk. And so this is the central server. Now, so what kind of servers are there? So there are fixed capacity service centers. The service time does not depend upon the number of jobs in the device. So this is most of the servers that we have in the computer systems are fixed capacity. All right. CPU may be modeled as a fixed capacity server. Then delay centers are infinite servers. The delay centers are one where there is no queuing, but the job spend same amount means same mean amount of time, regardless of the number of jobs in it. And so in this case, this is a delay server. Here, there is no queuing. When a job comes in, it goes to this system and it is served for whatever number of random time and then comes out. So delay centers are infinite servers. There is no queuing. Job spend the same amount of, probabilistically same amount of time. So this can be random, by the way. This delay centers don't have to be fixed deterministic time. And a group of dedicated terminals is a delay center. Third is a load dependent service center. Service rate may depend upon the load on the number of jobs in the device. For example, MMM queues would be load dependent servers. A group of parallel lines between two nodes in a network is another example. If you have two parallel links, then if there are two packets, they can go through, but if there are three packets, there will be queue. So MMM queues are parallel, load dependent servers. So there are three kinds of servers, right? There are more actually, but those three will do for us. Anyway, now just again another quiz. So if somebody gave you this formula, is this a product form network? That is the answer here, yes or no. Second thing is, these you have to fill in. Multi-core CPU, what kind of server it is? There are three kinds of servers. Remember this, right? So for each of these, fill it out quickly. And by the way, single core CPUs are of two kinds: dynamic frequency scaling and without and with. Dynamic frequency scaling, everybody understands what that is, that you change your rate. You are running at 2 gigahertz and then suddenly you start running at 5 gigahertz. Hard disk drives and solid state drives. Shall I come to the answers? Okay, so answers are, is this a product form network? The answer is yes. You know why? Because this is a trick. Basically, the thing is, this is just, it could go on the numerator. This is just another function of nm. So this is basically g, n1, n2, n3, nm minus 1, and nm. This is just a function of nm. And so this is a product form. Second thing is multi-core CPU. Multi-core CPU clearly is load dependent, is M server queue, right? No dynamic frequency scaling is fixed capacity. With dynamic frequency scaling, load dependent, because as the load increases, the CPU just changes its frequency, right? Hard disk drives are load dependent, but the solid state drives are fixed capacity, because in hard disk drives, you go next to wherever your head is, your reading head is, and so depending upon the load, the capacity rate changes. Whereas in the solid state drives, it doesn't matter, it is random access. Multiple users each handling one window. This used to be the old system where you had only one window, that was a delay center. But now when we are handling multiple jobs, multiple windows, you are a queue. You have a queue of jobs waiting for you. That part, multiple windows. Oh, okay. So, so now that you have Windows system, in the Windows system, when you are running 15 things at the same time, 14 things are probably waiting for you while you are doing one. Right? Maybe out of 14, maybe 3 are waiting on the disk and 2 are waiting on the CPU, but the rest of them are waiting for you. So you are a queuing center. Right? As opposed to in a single window system, you are just doing one, then you finish something, then it goes to CPU, disk, and everything else. When it comes back, you are again thinking about the same thing and servicing it. So there's no queue at you. In the F case, a shell. Yeah, window is actually, nowadays we have multiple windows only, right? But in the original days when there was no windows, there was only one box, command box, or whatever you want to call it, DOS box. So what it says is that, yeah, right. So basically it is saying several functions which are not functions. There are functions which are functions of N1 only, and there is no N2, N3 in there. Okay, hold on. and there is function of n1, n2, n3, all these multiply, and then all of these could be multiplied by another term which is a function of the total, and that's it. So there are total of m plus 1 function, m functions here and the 1 function here, right? And those m functions have the property that they just require you to know one variable, n1. And this one, these functions have the same property. Just these, in that sense, these are f functions. I mean, I have written g, but these are f functions. And this is the last one, because this also depends only upon nm and nothing else. Yeah, so actually, all of these actually could have, in these n is not explicitly stated. And so that is the thing, is that in this explicitly stated here, because it is n minus m, this function of n minus nm. So this is a function which is function of nm. This is a function. And in these cases, I haven't shown explicitly whether there is an n or not. And so in that case, basically what I should do is, maybe to be clear about this, indicate that these functions could have ni and then n also. F could have n, I, and n, because these functions would be different for different values of n. If in the whole system you have one user or two users, the function is different than if you had 200 users. So fi is some function of number just ISQ and n maybe, okay? And gn is only function of capital N. So move on to the summary. So we learned about the product form networks, and that's a big class, and the boundary has not yet been found. But Jackson started with a small class. BCMT increased it, and the Dunning and Busan increased it further, and people are still extending more and more. That's a big research topic for queuing theorists, to show that something new is also product form. And then we learned that there are three kinds of networks: open, closed, and mixed. And then obviously we learned about all these, and then we learned about three kinds of service centers: fixed capacity, delay centers, and load dependent. Now these are not, none of this is exhaustive, in the sense that there are other kinds of complications in the service centers, as well as other kinds of networks. Why I selected this particular subset of what is in the book is because this is what we need for the next chapter. Okay, and so with that, let's see the homework. In a series network of 3 routers. Okay, so this is a very simple thing. I mean, you already have the answer. Calculate the probability of having 2 packets with each of the routers. If this is MMM1Q, then all you have to do is, it's all, we already talked about the expression. You just have to use it.